Okay, everyone, your first set of notes. So here's the expectation. I expect that you have your own notes out, you have a pen or a pencil, and you're following along with me. If I'm writing something down in the notes, then you should be writing something down in the notes. You don't have to use my phrasing. You can say it in your own words, but I should be able to look at your notes and see that you have something jotted down for each of the items that we're going over today. So let's skip past the calendar and go on to page 5. And on the top of page 5, we see 2 columns here. We have acids and bases. So here's the first way to identify if something is an acid when you're given a chemical formula. So HCl, that is hydrochloric acid. And if it's in a chemical equation, we write it HCl, and notice that it has hydrogen in the front. Having hydrogen at the front of a chemical equation, not always, but often, will mean that it's an acid. Here's another example of this, H2SO4. Okay, both of these are acids, and then I can tell it's indicated to me because it has hydrogen at the front. Okay, another indicator that something is an acid is what you would expect. It has a sour taste if you can actually taste it, so it's sour. We also know that it has a lot of these H+ ions in solution. And that actually came from these hydrogens that are out front. They actually break apart, and we get a lot of these H+ ions just kind of floating around in the solution. Often those H+ ions will combine with a water molecule, and they turn into, so I'm going to say, or H3O+. And the fancy name of this guy, this H3O+, is hydronium. Other things that I need you to know about acids: they have a pH that is less than 7. Okay. And if you take a drop of an acid and you put it onto litmus paper, it will make that blue litmus paper turn red. Okay, now onto the bases. So for a base, in the chemical formula, it often ends with the polyatomic ion hydroxide, or OH. It's actually OH-, but we usually see it combined with a metal, so sodium hydroxide. This is a base, and what indicates to me that it's a base is that it has hydroxide, OH, at the end. Similarly, we could have a calcium hydroxide, which would be Ca parentheses OH close parentheses 2. Again, we have hydroxide at the end, and so those are bases. They have a bitter taste. They can be kind of slippery, like soap. Okay. And just like how the H+ broke off from these acids, the OH- is what breaks off. So we get a lot of these hydroxide ions in solution. They don't tend to combine with the water, though, and our pH is greater than 7. Then they do the opposite with the litmus paper. If I have red litmus paper and I put a drop of a base on it, then it turns that blue. Great. All right, now that's our basic definition of an acid and a base. There is a more precise one, which is called a Bronston-Lowry acid and base definition. And with Bronston-Lowry, an acid loses an H+. Okay, like it's going to lose an H+, where the base does the opposite. It's going to gain the H+. Now, we're going to talk more about this later, but a hydrogen atom is a proton and an electron. There might be some neutrons as well, but we have one proton and one electron. But if we lose that negative electron, it becomes an H+. So all that's left over is really a proton. So another way of saying lose H+ is proton donor. And it's not my favorite phrasing, but I know you might see it in the AP Chem test, and so I want to cover that. So they might call an acid a proton donor, and then here is a proton receiver. Okay, so we have our proton donor or proton receiver, but it just means that it's either going to lose the H+ or it's going to gain an H+. So look at this. Here is the hydrogen. And where the hydrogen goes, it's kind of hard to tell. It's right here. And this guy, this hydrogen, is gained by the water. When the water, the H2O, gains this H+, then it turns into H3O+. So this hydrogen and this chlorine, when they break apart, this H+ will break apart from a Cl-, because combined, then they're just neutral. And the H2O is going to gain that H+, and it turns into H3O+, and then we're left with the Cl-. So in this scenario, what's the acid and what's the base? HCl lost an H+. It's going to lose that hydrogen. So this guy is the acid. Now, what gained that hydrogen, or is going to gain the hydrogen? Right here, this is a base. With Bronsted-Lowry acids and bases, they turn into something. It starts as an acid, and then notice that this acid turns into Cl-, right? HCl loses the hydrogen and becomes a Cl-. And what the item turns into is the conjugate. There's the word conjugate. But it's the opposite. So if this is an acid, it turns into the conjugate base. Now, the water, H2O, turned into H3O+. And it started as a base, and it turns into the conjugate, and then it's the opposite. Instead of being a base, it's an acid. When we see the Lewis dot structures, we tend to get overwhelmed by this, and I don't want you to. Just rewrite it. It'll make it a lot easier. So see how this is a hydrogen and a chlorine? Well, this is just HCl. And see how this is H2? There's two hydrogens and one oxygen, so it's H2O. And this turned into Cl with a minus, and then H3O with a plus. It's the exact same thing. Just here's your chemical formula, here's the Lewis dot structure. And this is just showing how the HCl loses the hydrogen and it's going to be gained by the water. So it lost the hydrogen and the water gained the hydrogen. So as a quick reminder, if something is going to lose a hydrogen, it's an acid. And what it turns into after it loses the hydrogen, that is the conjugate base. And then if we have something that is going to gain a hydrogen, that's a base. And what it turns into after it gains the hydrogen is the conjugate acid. Okay, let's turn the page. All right, let's do one of these quickly together, and then we'll save the rest for class, just to remind ourselves. So I'm looking at this, and I'm asking myself, I see this H2SO4, but I say, what did it turn into? And this H2SO4 turned into HSO4. So it went from having two hydrogens to just having one. So this guy is going to lose a hydrogen, so it's an acid. Going to lose H+. And then notice that what it turns into, we always call it a conjugate, and then it's the opposite. If this is an acid, it turns into a conjugate base. And then I say, okay, what did the water turn into? Well, the water turned into hydronium, H3O+. And so if something is a base, that's because it's going to gain. It hasn't done it yet, but it's going to gain the H+. That's how I know it's a base. And then what it turns into is a conjugate, and then it's the opposite. If it started as a base, it turns into an acid. Okay, nice. We're going to save the rest of this page to do together in class. What is a mole? All right, we're on to page 7. Reminder that a mole is a counting unit, just like a pair or a dozen. Like if you have a couple, right? If you have a couple, then that means that you got 2 of something. And if you have a dozen, then you have 12 of something. Those are both examples of counting units, okay? Counting units means that it's the number, like the unit is the number, and it can be applied to anything. So I could have a couple of bunny rabbits. I could have a dozen bunny rabbits. But see how the number could go with whatever. I could have a couple of atoms. I could have a dozen atoms. But because atoms are so teeny, teeny, tiny, it's really helpful to have a counting unit that is an extremely large number, okay? So a mole, now, guess what? You don't have to have this memorized. I'm pretty sure I printed yours out in green, but this is your reference. So we have our periodic table, and if you turn the page, then we have a bunch of info right here. And one of the pieces of info we get, atomic structure, go to the other side, Avogadro's number. Avogadro's number is 1 mole. So 1 mole, if you have a mole of something, you have 6.022 times 10 to the 23rd of those things, okay? So if I have a mole of bunny rabbits, then I have 6.022 times 10 to the 23rd bunny rabbits. I'm pretty sure if you took all those bunny rabbits and just combined them, that they would be roughly the size of the moon. That's a lot of bunny rabbits, okay? So that's what a mole is. Now, what I also want you to remember about a mole and a couple and a dozen, these counting units, is their size is dependent on the object, meaning not the size of the number, but all of these beakers contain exactly 1 mole. But the copper atoms, 1 mole of copper atoms, is so much smaller than the 1 mole of sugar molecules. And wait, if I have a mole of this and a mole of this, then why is this one so much smaller than that one? And it's because the items are smaller. So I could have a dozen tennis balls and then a dozen basketballs. There's still a dozen in both. It's just one was larger than the other. The item itself was larger. So the sucrose molecule must be much larger than the copper atoms. Okay. Concentration. We didn't get a lot of time with this in Gen Chem and Honors Chem, but the good news is that it's really easy. So concentration is how much stuff there is in a given volume, okay? The units of concentration is moles per liter. So maybe this has 2 moles in this 1 liter of material, and this only has 1 mole in this 1 liter of material, right? That would mean that this one is twice as concentrated as that one. Now, I haven't counted these up, obviously. This one may even be, it looks even less than 2. But that's what concentration is. It's the amount of moles per liter. Now, this equation for concentration is also in your reference. I'm going to show you that in just a moment. But often, I'd say the vast majority of the time, they take this moles per liter and they call it molarity. Capital M, molarity. So I might ask you, I might say, hey, what's the concentration? You need to figure out how many moles there are and divide it by how many liters. Or I might ask you, hey, what's the molarity? And I'm just asking the exact same thing. Concentration and molarity are the same. How many moles per liter? Okay. Okay. Let's do one problem together. You dissolve 0.5 moles of NaCl. Oh, sorry. Pause. Back to your reference, just so you know where this is at. It's still that like front of the reference, and it says gases, liquids, and solutions. And right here, it has a capital M, and if we forget what the capital M is, then we check over here. It's not bold, so it's molarity, or concentration. N solute, so let's see, N, O is the number of moles, that makes sense. And then L, solution, go, okay, great, liters of solution. It's funny that they didn't give us that one, but that's okay, you guys will know liters. So it's the moles per liter. Now, I was just told in this problem that I have 0.50 moles of sodium chloride, NaCl. So I'm going to write that down. You dissolve 0.5 moles of sodium chloride in enough water to make 2 liters of solution. So my liters, or my volume, is 2 liters. What is the molarity, or the concentration? Okay, molarity is moles, 0.50 moles per liter. Oh, and it's 2 liters. Great. Okay, so I take 0.5, divide by 2, plug that in my calculator, and I'm getting 0.250. But wait, hold on. Significant figures. Leading zeros are not significant. Trailing zeros are only significant if the number has a decimal. So that means that this first number is 2 sig figs. And then right here, both of those are trailing zeros. They came after the first or the last, like, non-zero digit. So those are both trailing. This would be 3 significant figures. So this is 2 sig figs, that's 3 sig figs. So that means my answer can only be 2 sig figs. So my concentration or molarity, 0.25, because leading zeros are not significant, so that's 2 significant figures. What units should I put? You have a choice. You can either put moles per liter, completely fine, absolutely correct. Or you can write capital M for molarity. Great. And then during class is when I'm going to want to go over concentration questions with you guys. So let's keep going. All right, we talked about this first part on page 9 a little bit already, but here's what I really, really want you to know. I want you to know that in AP Chem, anytime you see H+, you can replace it with hydronium, H3O+, or vice versa. Doesn't matter, okay? Anytime. And the reason why is when H plus is aqueous, when we dissolve it in water, okay, aqueous, it often, almost always reacts with a water molecule. And when it reacts with the water molecule, let's make that guy a liquid. Sorry, that's a little lowercase l, liquid. Then it turns into this hydronium, the H3O plus, aqueous. So as we move into this unit, these are interchangeable because it's always going to be in water. So if it's easier in a situation to have it be H plus, then change it to H plus. If it's easier in a situation to have it be the hydronium, the H3O plus, then change it there. If I look at my reference and I turn the page, you'll notice underneath equilibrium, I see H3O plus. It's completely fine to change all of those just to H plus, if that's easier. Okay, more on that later. We talked about the pH scale already a little bit as well. When it's 25 degrees Celsius, so at roughly room temperature, a pH of 7 is neutral, okay? This is neutral, great. When we have a pH, notice we have pH and we got pOH. When we have a pH that is less than 7, then we are acidic. And when we have a pH that is greater than 7, then we're basic. Now, we know what this means, that there's either a lot of H plus in the solution or OH minus. It's cool because neutral at 7, do you see how it's like equal amounts? Like here's how much H plus there is, and here's how much OH minus. When these things are equal, then we are neutral, and that has a pH of 7. Really cool. Well, I have another thing though, which is pOH. So pH, the more acidic something gets, which means the greater the amount of H plus, okay? Like the higher the amount of H plus, the lower the pH number, right? This is more acidic, this is less acidic. But notice about the pOH. If we're gaining H plus, which means that we're going this way, our pOH is getting bigger. Then we could have the opposite happening. What if we increase in the amount of OH minus, okay? And that would be becoming more basic. Well, as you become more basic, your pH increases, but your pOH decreases. We're going to be using these arrows for relationships a lot. If you can recognize these relationships, it's really going to help you. So concentration of H plus, this is directly proportional to pOH. It's inversely proportional to pH. The other cool thing is that at 25 degrees Celsius, if you take the pH and you add it to the pOH, then it's going to equal 14 each time. Only at 25 degrees Celsius. If it's any other temperature, this doesn't work anymore. But yep, each time, if you take pH and pOH, so here's equilibrium, here is pH, here's pOH, and it says at 25 degrees Celsius, pH plus pOH will always equal 14. All right, now, this is just another representation of this. I don't think we need to write a lot down here, but I do think you need to understand this. So see how there's a lot of H plus and there's a small amount of OH minus? That means it's acidic, it has a lower pH and a higher pOH. When you have brackets around something, Like, do you see these brackets around the H+? The brackets mean concentration. And maybe we should quickly put that back on the concentration on page 7. Brackets mean concentration, or the amount in a given volume, right? So here, the concentration of H plus is big, right? 0 compared to like -14. So there's a lot of H plus, there's a small amount of OH minus. Then they're equal, we have the same concentration, and they have a pH of 7. And then when we have a lot more OH minus, this hydroxide, and a small amount of H plus, then it's basic. Oh my goodness, I've never seen, that's so funny. I added this image. I've never seen it spelled like that before. Cool. Alrighty, and I think one of the last items is you need to know the big 6 strong acids. In AP Chemistry, if an acid is anything other than the big 6, then we consider it a weak acid, okay? So, yes, you need to have these memorized. So, for all of these, what's really cool is that whatever the concentration or the amount of the strong acid is, it is going to equal the concentration of that H+. And that's true for every single one of these. Whatever that concentration is of like the HClO4, then that's going to be the concentration of the H+. Okay? So how do we go about memorizing this? First off, recognize that all of them have hydrogen at the front. Only one of them has 2 hydrogens. Okay? And I have another way to help me with the first 3. Do you see how it's HCl, HBr, HI? So if you look at your periodic table, Cl, Br, and I are all in a row. So if you put a hydrogen in front of this one, and this one, then those are 3 of your 6 strong acids. The other thing is you need to know your polyatomic ions. I know that was last year, and we're going to work on it. We're going to remind ourselves about this in the next unit. But there were polyatomic ions. Here's one of them, NO3-. The name of that guy is nitrate. And if you put hydrogen in front of nitrate, you get nitric acid. If you take ClO4-, that's chlorate. And if you put a hydrogen in front of that, then you get hypochloric acid. Oh, I need to double check the name. But you get a strong acid. And then there's sulfate, SO4, 2-. Now, because it's a 2-, that's why we need 2 of the H pluses to go in front of it there. So those are your big 6 strong acids. Yes, you need to have these memorized. Yes, I am going to be testing you on them. All right. I think that's a good wrap-up spot. When we get to class, I want to talk to you about just this section, only this section, and then we'll go over those problems like on page 8 and on page 6 that we skipped. We'll go over those together to make sure that you guys understand it before we dive into practice in your groups. Hey, I'm really excited that you're in AP Chem. So guys, it's going to be an amazing year. I'm really looking forward to working with you and helping you. So if you need any help at all, don't hesitate to ask. Okay, see you in class.